All right, we're back. This is Techmath1. We're looking at chapter 6, specifically 6.9. That starts on page 263. And so we're talking about precision and absolute error. So precision is pretty easy. Precision is just tell me how many decimal places you're going. It's or if it's whole numbers or hundreds or just the end place. So this is tenths. That's precise to tenths place. Tenths, hundredths, thousandths. That's precise to thousandths place. Tenths, hundredths, thousandths, ten thousandths place. Tenths, hundredths, thousandths, ten thousandths, hundred thousandths, millions place. Dr. Evil, millions place. Okay? So that's all precision is. Precision is basically what decimal place it is. And this has more precision than this, and this has more precision than this, and this has more precision than that. This is the least precise, this the most. All right? When we talk about limits, you're going to want to go one place farther and put like a 5 or take away like a 5. So look, if this was $43.80, because it's the tenths place, then I would take away a nickel and I would add a nickel. So it would be 43.75 for the lower limit and 43.85 for the upper limit. And when we talk about like absolute error, then that's just how far from this to that. So that's 0.05. It's a nickel. So it isn't from the boundaries. It's not from the limit, the lower limit and the upper limit. It's from the number to the lower limit and the number to the upper limit. So that's why it's 0.05. All right? If this was my measurement, it was a whole number. When we look at like 78 and I wanted a lower limit, what I would do is I would subtract 0.5. So if it was a whole dollar, I would subtract off 50 cents basically and add 50 cents. So it would be 24.5 and 25.5 for the lower and upper limits. All right. If it was $1.84 where it went to pennies, I would actually go to pennies, a half a penny. And so I would go to thousandths place out, but I'd subtract it and add it. So that one, maybe I'll write it out for you here. 1.84 minus 0.005. Notice I went to two places, tenths, hundredths, and then I went to thousandths place, always with a 5. All right, and so then we get 1.835, right? And 1.845, because it would be 1.84 plus 0.005. So that's a little easier, 1.845. Those are the limits. What about like number 80, where it's not only a whole number, but it's all the way to thousands place? Well, then if you were thinking hundreds place, you'd be right. So half of 1,000 is 500. So I would subtract that away from that, 28,250. For my lower boundary, subtract 500. And then for my upper boundary, add 500. That's a lot easier to do, 283,500. So those are our lower and upper boundaries. And absolute error is just the little bit that you tacked on and took off. All right, let's look at significant digits, 6.10. So when we talk about significant digits, we're changing from precision to accuracy. Lots of people use those as interchangeable. They are not interchangeable. Precision and accuracy are different. So let's take a look at 88. And that's a whole bunch of examples. 0.83, 5.70, 0.0025, 160.0, 65.000, 0.0903, 176,000, and 9,000,000, 9 million. But then they also have a weird mark on here. There's an underline under the thousands place. All right. So significant digits, if they're just numbers, they're automatically significant. Oh, also, I was lazy here. I didn't write down the 0 in front here. I could put them on there. That isn't really a math thing. That's more of a typeset thing. People will type 0 point blah, 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 0 point blah, 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 0 point blah, blah, blah. And most of the time that I write it down, I never do that. The reason that they do that is that's more of a typeset thing. They want to throw a 0 out there so you pay attention that there's a decimal point there. That's all. So it's not really a math thing. It's more of a typing thing. All right. Now, significant digits. This has 2 significant digits. If they're just numbers, it's automatically significant. So if I did 1, 2, 3, 4, 5, 7, 8, 9, 12, all numbers, no zeros, you just count up each one of the numbers and that's how many significant digits it would have. So automatically, if it's not a 0, it's significant. Now, there's all these rules about this. 5.7, and then they added a 0 where they didn't need one after the decimal. That counts as significant. So this is 3 significant digits. 0.0025. Now these guys don't count. They are after the decimal, but they're not after the number on the decimal. So if I would have went 0000, then all of a sudden it would have 5. But since these 2 are before it, this is only 2 significant digits. Another one, let's look at a really small decimal. What if it was like this? And then a 1/8. All of those zeros are not significant. The 1/8 is. So that only has 2 significant digits. Even though it's got all of those other numbers, those zeros don't count. Same with really large numbers. If I go 9 billion, that's only got 1 significant digit. All those zeros after don't count. Unless they do the little underline trick. If they underline any of these, it becomes significant. So if I put a little underline on that one, all of a sudden that's significant, and then the other 2 captured ones are significant. So if it's between 2 significant digits and it's a 0, it is significant. All right, so like this. Because they put a 0.0, this one becomes significant, which means this one is. So there's 1, 2, 3, 4. So this 0 is captured by 2 significant digits. If it's between 2 significant ones, that 0 becomes significant. That would be 5, because they're all significant after the decimal. If they add them, and you don't need them really. Not significant, significant. So this one's a little tricky. 3. This does not count as significant. That's just like a revving up to the real number thing. And so that one only has 3. All right. 2, 3, 2, 4, 5, 3. Okay, just double checking. That's 3. Because there's 176,000. These are not significant. And now this one is weird. This would be 1. This would be 1, but they underlined the place in the thousands, the 0 in the thousands place. So that becomes significant. You got to treat it like like it was a 7 or a 9 or something. And so that means these 2 are significant because they were captured by 2 significant digits. So this is 1, 2, 3, 4. 4. All right. And now you might say, well, why are we doing this? This is weird. And well, this is accuracy. The more significant digits, the more accurate. That counts as a sign of accuracy. So if it was 9 billion compared to 160.0, this one is more accurate than that one. Because that only has 1 and that one has 4. All right, most significant digits wins for accuracy. If it's a tie, I'll show you what we'll have to do. when we get there. All right, so let's get 93. Round to 3 significant digits. Okay, so they give us numbers and then they tell us to round 9.9984, and I have to round that to 3 significant digits. Well, if I rounded this number, it would be, if I just rounded it to the 8, that would be 4 significant digits. So I got to round it to that. Well, that bumps to a 10, to a 10. So it's this, it's 10. But if I write just 10, that's only 1 significant digit. So I have to fix it. They want 3 significant digits. So I would add 0.0. Now this is significant because it's after the decimal and I didn't need it. And so if that's significant, that one gets captured. So 1, 2, 3. Now it's got 3 significant digits. Okay. All right, let's look at the second one in there. They give you a 0.9999. It's a lot of nines. 4 nines and a 5, 6. And they want 4 significant digits. So again, we're in the same kind of problem. If I take that 5 and I try to get it to there, that bumps it all the way up to 1. All right, well now it's 1, but that's 1 significant digit. If I go 1.0, that's only 2 significant digits. They want 4 significant digits. So what I can do is, I don't have to do the little underline trick. That's only if it's whole numbers. With decimals, as long as I keep adding them after the decimal, where there's no numbers there or anything, that becomes significant. So 1.000 is 4 significant digits. All right. Okay, so now let's look at relative error. Relative error on 611, we do that if it's a tie. And again, I worked out the worksheet, the precision accuracy worksheet. I made a video up for that homework assignment specifically, because there was some tough problems on there. And so if this is still a little fuzzy, watch that video also. Okay. All right, so we're looking at 611, relative error. Let's look at 96. So relative error would be, let's take a look. Let me show you how to find that. You take the absolute error and then you divide it by the number itself, and that'll be the relative error. So look, remember how we did the limits on this? We if it was 47, we would take away 50 cents and add 50 cents. So the limits on this would have been 46.5 to 47.5. That would be the lower limit and the upper limit, and the absolute error is 0.5. So we actually take that 0.5 and then you divide it by the original number, and that'll give you the relative error. So this is relative error, 0.0106. So that's got a relative error of that. Now let's look at another one. So if it had 2 significant digits and another number had 2 significant digits, and I wanted to know which one was more accurate, this is what I would do. I would find the relative error, and the one with the smaller relative error is more accurate. All right? They don't throw 1 at you, they throw 3 significant digits. So this is automatically more accurate than that. So now think about it. It's tenths, hundredths. I want to go to 1,000, so I go 0.005 is going to be the absolute error, and then we divide that by the original number. So basically, if you want just an algorithm, it's however many decimal, whatever the decimal point is, or the last number is, you go to the next one and add a 0.5. So look, tenths, hundredths, I put zeros there, and then I just add a 5 into the thousandths place. That's how it's always going to be, okay? And so we divide those, and this has a very small relative error. Okay? And so let's take a look at number 100. That is, they give us two things with the same amount of accuracy according to significant digits, but then they want us to identify who's. Oh no, never mind. We don't have to do relative error on that one. Okay. This one's a lot easier. So we've got that, or this. Those are the two that we're going to compare. Letter B. This is number 100 on page 272. So letter B is 2.77 or 0.1825. Letter C is 0.0059 or 4.05. And letter D is 0.700 or 0.0097. And they want us to identify the most accurate one. Which one is more accurate? So to do that, you just look at significant digits. So 1, 2, 3, 4, 5 significant digits there, and 1, 2, 3, 4 significant digits there. This one's more accurate. Three significant digits there, 1, 2, 3, 4 significant digits there. The one with the more significant digits is more accurate. 2 compared to 3. 3 compared to 2. Okie dokie. So when it's one of them has more significant digits than the other, it's super easy to determine accuracy as long as you can get your head around what a significant digit is. So where does it get a little blah? Well, right now it's going to get a little blocky. Let's take a look at the last one in this section I want to look at is 104. And so they give me all of these numbers across the top. 159.3, 0.675, 2.03, and 0.0069. So this one has 4 significant digits. That one has 3. That one has 3. And this one has 2. So most accurate. And then the next, and then the next, and the least accurate. Okay, so most and least are easy. Most accurate. Most significant digits. Least accurate. Least significant. Both of those have 3, so that presents a problem. So what we're going to do, tenths, hundredths, thousandths, we're going to go 0.000, tenths, hundredths, thousandths, add the 5 after it's in the 10,000ths place, divide that by 0.675, tenths, hundredths, so tenths, hundredths, and then add a 5. And divide that by 2.03. And so now, when we do this calculation, that's going to determine whichever one is smaller is more accurate. It's got a lower relative, this is once again called the relative error. So if it's got the smaller relative error, that's the one to go with. So let's see, 0.0005 divided by 0.675 is 0.000747. And here, let me show you on the calculator what the readout is going to look like. When you divide those, the calculator throws it into scientific notation. So that little e to the -4 means take that decimal place, and move it 4 places left. That's why I did 0.000747, okay? So that is the relative error for this number. This one is 0.005 divided by 2.03. That is 0.00246. So this one, tenths, hundredths, thousandths, and then 7 is smaller than this one, tenths, hundredths, thousandths, right? Where there's a number there. So this one is smaller. Smaller relative error means more accurate. So 0.675 goes there, and 2.03 goes there. All right. Given these measurements, wait a second. The most accurate is, the least accurate is, oh man, they didn't even want me to do that. You guys, I'm sorry. I didn't read the problem carefully. They wanted the most accurate and the least accurate. Which is 159.3 and 0.0069. And then they wanted the most precise and least precise. I was looking at it going, what the heck did they do? Well, precision just is based off of, right? Most precise is going to be the 10,000th place. And then the least precise is going to be the 159.3. So they did make that actually quite easy. I'm so glad I explained this one. This is the most accurate to least accurate of all 4. And so it gave me a chance to explain relative error to you. We found those in problems, but we didn't really apply it. So now that's been applied. But this is what's actually in the workbook. They just want most accurate, most precise, least precise. See? Yeah, that's okay. We got a little extra bang for the buck here. The last video is going to be 612.